Welcome back to The Explainer. Today, we're dissecting the underlying mechanics of machine learning. Instead of treating artificial intelligence like some impenetrable black box or, magic, we're pulling back the curtain. We want to see exactly how these foundational systems actually learn. For those of us navigating today's tech landscape, understanding the nuts and bolts of this field isn't just interesting, it's absolutely essential. By the end of our time together today, the actual machinery driving these algorithms is going to make a whole lot more sense. Let's jump right in. So what if I told you AI does not start smart? I know, we see these highly capable, seemingly brilliant systems out in the wild, and it's super easy to instinctively assume they were just born intelligent, right? Like they were pre-programmed with this vast repository of knowledge right out of the gate. But that couldn't be further from the truth. The genesis of an AI model is actually surprisingly humble. The reality is that it starts completely clueless, literally a blank slate. It has zero innate wisdom or intuition. Instead, through the precise architecture of machine learning, it slowly digests vast amounts of data. It observes variables, it processes information, and it rigorously adjusts its internal parameters until its outputs feel highly intuitive, even brilliant to the end user. So there's no innate genius here at all. There is just a highly optimized, extremely powerful learning process.
Okay, let's dive into Section 1, the big shift. Moving beyond handwritten rules.
To truly grasp how this works, we have to look at the fundamental difference between traditional programming and machine learning, because this represents a massive paradigm shift in how modern computing fundamentally operates. Think about traditional programming for a second. A human developer sits down and dictates every single rule by hand. You tell the computer exactly what to execute in every conceivable scenario. Basically, if X happens, do Y. But machine learning represents a completely inverted approach. You simply show the machine thousands or millions of examples, and you let it discover the rules itself. The system infers the logic based on the data provided. That is the big shift, and it is exactly why machine learning has unlocked capabilities that traditional coding simply couldn't reach. So, how does that rule discovery actually take place? Let's move to Section 2, the core learning loop, how learning actually happens. We need to look at the engine that drives all modern machine learning systems, and it all boils down to a fundamental four-step sequence. First, you feed in the input data. That's your raw information. Second, the algorithm studies that data, hunting for statistical relationships. Third, based on that rigorous study, the system builds a model. You can kind of think of the model as the refined mathematical representation of what it just learned. And fourth, that model is deployed to make predictions on new, unseen information. The machine is actively building a framework of patterns that it can generalize to solve future problems. That continuous loop powers the entire landscape of AI, which brings us to Section 3, 3 ways machines learn, the family of ML methods. You see, machine learning isn't just one monolithic trick. It's a diverse family of methods falling into 3 distinct buckets. The first style is supervised learning, which is learning with answers. You give the machine examples where the correct result, the label, is already explicitly known. For example, you feed it thousands of images labeled either cat or dog, or you give it a million emails labeled spam or not spam. The model makes a guess, calculates the distance between its guess and the correct label, and then adjusts its internal weights to improve its accuracy for the next time. In direct contrast, we have unsupervised learning. This is learning without answers. Here, the machine gets a massive data set, but absolutely no labels are provided, none. So it's forced to find hidden structures entirely by itself. And in the real world, this carries massive weight. A system might analyze millions of credit card transactions to detect highly unusual fraud patterns, or it might cluster similar consumer purchasing behaviors together to uncover groups that human analysts completely missed. It's discovering the shape and topology of the raw data completely independently. The third method is reinforcement learning, or learning by reward. The AI takes an action in an environment, gets feedback, and learns strictly from its successes or failures. It is essentially training through highly accelerated trial and error. If you've ever seen AI master complex strategy games like Go, navigate a physical robot through an obstacle course, or optimize advanced supply chain control systems, you are looking directly at reinforcement learning in action. Now that we know the 3 core methods, let's turn to Section 4, the training process, turning data into predictions. We really need to bridge the gap here and understand the mechanics of how raw information transforms into a sophisticated predictive model. So the crucial point is, to train a model effectively, you need three essential ingredients working in tandem: features, labels, and a massive amount of data. Without all three of these tightly integrated, the system simply cannot build a reliable mathematical representation of reality. Let's break down those first two terms to clarify how a machine categorizes incoming information. Think of features as the specific characteristics the model studies. They're the inputs, the independent variables. Labels, on the other hand, well, they're the outcomes. They are the correct answers, the dependent variables that the model is ultimately trying to predict with high confidence. And that brings us to the most critical ingredient, the data itself. There's a foundational rule here. If the data is poor, the model learns poor patterns. I literally cannot emphasize this enough. Because the machine is learning entirely from the historic examples we feed it, data quality is absolutely paramount. If you feed it biased, incomplete, or noisy information, it's going to diligently learn those exact flaws, resulting in heavily skewed outputs. The model is only as good as the information it consumes. All right, let's take this from the abstract to the real world in Section 5, Build Your Own Model, from abstract to real. I want you to mentally design your own simple machine learning problem right now. Pick a specific prediction task. Will a customer renew their enterprise software subscription? Is a financial transaction fraudulent? Will a specific component in a jet engine fail within the next 30 days? Let's actually walk through a universal sample task together to see the architecture in practice. We'll use the classic forecasting question: will it rain tomorrow? If we want our machine learning model to answer this question with rigorous accuracy, what exact elements do we need to provide? To answer that, we map out the logic. For the historical data, we collect localized metrics: temperature, humidity, cloud cover, and wind speed. Those specific, measurable weather conditions serve as our features. Our label is simply the historical outcome. Yes, it rained, or no, it didn't. The model ingests thousands of past examples of these features and mathematically maps out the correlations. It calculates that, hey, when the humidity feature spikes and the barometric pressure feature drops, the probability of the yes label skyrockets. It is turning empirical data into reliable predictions. Which brings us right back to our core thesis. Machine learning is not magic. It is highly logical, structured pattern learning powered entirely by data. Whether we're utilizing supervised learning to categorize information, unsupervised learning to map hidden topologies, or reinforcement learning to navigate dynamic environments, we are simply applying statistical rigor at a massive computational scale. But this leaves us with a critical, lingering question. If the process is this structured and mathematically grounded, why can smart-looking AI still fail so spectacularly? What actually happens under the hood when a model faces a completely unprecedented situation in the real world? Keep that provocative thought in mind as we prepare for future explainers detailing how these models are rigorously evaluated and where they ultimately break down. Until then, stay curious.